Okay, good morning everybody. Welcome back to Math 115. So today we're going to review for the exam. So as usual, the protocol for that will be that I have some stuff that we can work on, but before I jump in and talk about that stuff, what I'd like to do is ask you guys if during your studying you've come across anything particularly confusing that you'd like to discuss now. And then if you have any problems prepared, we can do those problems. Or if you just have a general idea of something that you're confused about, I can provide you with a little bit more information in that vein. So yeah, without further ado, I guess let's just jump into it. And if anybody has anything, please do share. You can either speak up on the microphone, or you can type your questions out in the chat. Meanwhile, I'll get the Notability up and running. I guess we'll just use this. Sorry, we're going to have to be in light mode today, because this is where I have my review materials. Nobody has any particular questions they want to ask? Here we go. Sure, can we do some examples with arc sine, arc cosine, and arc tangent? No problem. Let's see if I can find some in here. I thought I had some in here. Here we go. Okay, so we'll focus in on this problem number 4. And maybe before we start in on actually computing arc sine and arc cosine, let's review what these functions actually are and what their purpose is. Okay, so let's add a page. And we definitely need to change that paper. Okay, so the arc sine function is a function whose input x is a value which sine takes, i.e. a y value of a point on the unit circle. The output is then the unique angle theta such that two things are true. The first thing that's true is that theta is going to be between negative pi over 2 and pi over 2. And the second thing that should be true is that sine theta equals x, our input. Okay, so this x up here is the same x down here as should be the output of the sine function under this angle theta. Okay, so this is what the arcsine. Okay, another question coming in. I can address that really quickly. The question is, how many questions will be on the final? I don't know. Probably more than usual. So I typically put like, I don't know, 5 to 7 questions on the exams. The final exam will probably be more like 9 or 10 questions, somewhere in that range. So a little bit more, but not excessive. Okay. So carrying on with this discussion. So this is what the arcsine function does. Okay, so let's interpret what this means in terms of the unit circle. It says, if I'm dealing with arcsine, first of all, I'm only going to care, well, let's describe why we're only going to care about the right half of the unit circle. It's going to be true that we're only going to focus on this right half, but let's describe why. Okay, the goal of the arcsine function is for the input to be a y value of a point on the unit circle. So if you describe to me a specific y value, such as this y value right here, this is maybe the line, I don't know, y equals to some number. Don't know what that number is. And you ask me to find the point on the unit circle which intersects this line, and then tell you the angle theta of the angle which we put in here, which points at that intersection. Well, I'm in a little bit of a quandary because there's more than one point which is on the unit circle which intersects this line. There's a point on the right half of the unit circle and a point on the left half of the unit circle. And so I come back and say to you, well, do you want me to tell you what this orange angle is, or do you want me to tell you what this green angle is? Those are both going to be angles which satisfy the property that sine of theta is going to be equal to this number that we have specified, and it's also going to be true that sine of theta is equal to this number where we're talking about the orange angle. Okay, because both of these points have the coordinates, well, this one will be the point coordinate x comma y, and then this will be the coordinates x comma negative x comma y, but they have the same y coordinate, which is the key issue here, which is where the second condition comes in. The second condition says, I want sine theta to be equal to x, yes, but I know that there are two answers to that question, so I'm going to narrow my range of focus to just the right half of the unit circle. And this is saying, well, I really want the one on the right half of the unit circle. Okay, so this is how arcsine works. Okay, so let's do maybe a practice. So let's try this one, where we're supposed to find arcsine of 0. So arcsine of 0, how would we do that? Well, we know that really what this is saying is find angle theta such that sine of theta equals 0. And 2. Theta should be between negative pi over 2 and pi over 2. Okay, so this is our goal. Okay, so we're going to focus in on the unit circle. And I know since I'm working with arcsine that I should focus entirely on the right half of the unit circle, and I'm going to ignore the entire left half of the unit circle. And what does this first condition say? This says sine of theta is equal to 0. Sine of theta is the y coordinate of the point on the unit circle. So what I'm going to do is I'm going to have a point here somewhere on the unit circle. And my point is going to be somewhere along this right half of the unit circle. And what sine of theta is equal to 0 is telling me is that the y value of the point should be 0. Well, the y value tells me how far up and down I'm going, and basically the x value is going to be unspecified. So this point, whatever it is, it should have the form, the point should have the form x, where x is some coordinate, which we don't know what it is yet, and then the y coordinate should be 0. Okay, which means that essentially we should be somewhere along the x-axis. Okay, that doesn't go over the x-axis. Somewhere along the x-axis here. Okay, so this point here, I'm going to put it right there, where I can see that the y-coordinate of that point is going to be 0. Now, what am I supposed to do now? I'm supposed to provide the angle theta, which is between negative pi over 2 and pi over 2, such that the angle theta points directly to the right. So let me ask you guys, what do we think theta should be in this case? Pi over 2 is suggested. Does everyone agree? Theta equals pi over 2. Okay, we might need a little bit of review on how we measure angles on the unit circle. The way we measure angles on the unit circle is that we have put our initial side facing straight to the right. And then the angle theta gets measured in the following way. We just measure basically up from the initial side. Okay, so what we're going to do, oh, that's not going to work. Why don't I? What we're going to do is we're going to measure the difference between the directions of these two rays here. Okay, we're going to measure the difference between the directions of these two rays. So the initial side is always starting directly to the right. Okay, so if I have an angle which is facing directly to the right, then it turns out that the terminal side is going in the same direction as the initial side. So if I want to talk about the difference in the direction between these two rays, there's actually no difference in their direction. So the difference in direction is 0. Okay, difference in direction is 0 if we're facing directly to the right. Okay, so now I'm going to draw in a couple more key ones that you guys should know, and then the rest I'll leave it up to you guys to fill it in. This one here is pi over 2, or 90 degrees. Facing, oh, that doesn't show up very well. Facing directly to the left is pi, or 180 degrees. Facing directly down is 3 pi over 2, or 270 degrees. And then so on and so forth. Okay, so if you want to be halfway somewhere in here, then this halfway point, okay, is going to be 1/2 times pi over 2, which is pi over 4, right? And so on and so forth. Okay, you can split it into thirds as well. So here's also pi over 6. And then here's pi over 3. Okay, and you can split each of these into these different things here. Okay, so if I wanted to express the angle measurement of an angle which starts facing directly to the right and ends facing directly to the right, then the initial side and the terminal side are the same. So there's no difference in their direction. And so theta should be equal to what? Would be equal to 0, right? I think Sam put it in there. Mitchell and Heidi, are we kind of on board now? Does this make more sense? How we measure these angles? Okay. This is a pretty important thing to know for the exam. So if you need a little bit of review with that, you might want to go back to the kind of first lecture where we started talking about angles and how we measure them, because that's kind of critical, mission critical for the trig stuff. Okay, so in this case, the angle theta which we were looking for is 0. So it turns out arcsine of 0 is just equal to 0. Okay. Arcsine of 0 is equal to 0. Okay, let me pause for questions about the arcsine problem. So we saw the definition of arcsine. We saw why we should really be focusing only on the right half of the unit circle. And then we actually solved an arcsine problem. We found an angle theta such that these two properties were satisfied. Sine theta should be equal to the input, and theta should be between negative pi over 2 and pi over 2. So we put the point on the unit circle whose y value was the input, and then we just found the angle theta which points in that direction. And the angle theta which points in the right direction, to the directly to the right, has measurement 0, since we measure an angle from the positive x-axis. So if our terminal side is the same as our initial side, then the angle measurement is 0. Okay. Any questions about this stuff? Or was there any part of this that was particularly confusing? Maybe you guys can't even really see that well now that I'm zoomed out so far. Okay, maybe let's have the arc cosine now. Well, arc cosine is going to be basically, you know, it's going to come in this same exact package. So let me copy all of this. And arc cosine, we're only going to need to modify it a little bit. So here we have arc sine. So I'm going to replace arc sine now by arc cosine. Is a function whose input x is a value which cosine takes, i.e., not a y value of a point on the unit circle, but an x value of a point on the unit circle. Then the output is then the unique angle theta such that two things are true. First of all, cosine of theta should be equal to the input. And theta should now be between 0 and pi. Why is this true? Okay, this is true for the following reason. If I have my unit circle, now I'm going to explain why we only focus on the top half of the unit circle when we're doing arc cosine. Well, arc cosine says, you give to me an x value. Okay, and you say, well, here's an x value. Let me draw it in green. Here's an x value, and an x value makes a vertical line. And you ask me, find the point which this vertical line intersects the unit circle on, and tell me what is its angle theta, which is pointing at that point. And I come back at you and I say, well, your question makes no gosh darn sense because there's actually two angles, theta, which point at two different points which satisfy the requirement that you gave me. So which one do you want me to, which angle do you want me to provide? And you say, well, there's only one point on the top half of the unit circle which is going to intersect any vertical line. So just give me that one. So we only focus on the top half of the unit circle. So the angle measurement should be as follows. So if you check out my purple line here, my purple line starts facing to the right, and it should be somewhere in this region, okay? Now 0 degrees is facing directly to the right, pi over 2 is facing directly up, and pi is facing directly to the left. Okay, so 0 to pi exactly describes all the angles which point at points on the top half of the unit circle. So that's arc cosine. Okay, so let's solve the next one. The next problem was to find out, well, what is arc cosine of 0? Okay, so now what I'm going to do is I'm going to take my unit circle here. And I know, again, I'm only going to focus on the top half of it. And what am I going to do? I'm going to put a point somewhere on this top half of the unit circle. And this 0 in here is telling me what the point should be. It should have the form 0, comma, some number. Okay, so the x-coordinate of the point, which I put on the unit circle, should be 0. Now the x-coordinate describes how far left and right I go. So if I want to find this point, where should it be? Well, it should be facing directly up, right? Because then this, let me move this up here. Okay, come on, bring my dot with me. Okay, then this point should be right here, right? Because that's where the x value is 0. We don't go left and right at all. And we actually know what the y value of that point is. It's going to be 1. Okay, so now what am I supposed to do? I'm supposed to give you now the angle theta, okay, which points at the point 0, comma 1. So I measure my initial side is facing directly to the right, and my terminal side is facing directly up. What kind of angle is this in here? What kind of angle is this? That's a 90-degree angle. It's a right angle, in fact. We can draw it with a corner. So this angle is 90 degrees. Of course, when we do arc cosine, the outputs the angle in terms of its radian measure. So we should make sure that we convert this to radians by multiplying by pi over 180. And that would get me pi over 2 radians. Okay, so the output of arc cosine of 0 is pi over 2. Okay, so this is the difference between arc cosine and arc sine. Is now, instead of focusing on the right half of the unit circle, we're going to focus on the top half of the unit circle. Any questions about arc cosine? Seems like no. Okay, so I'll tell you about the hardest one, arc sine, or arc tangent. So first let me do copy again, and I'm gonna replace now by tangent. Okay, so arc tangent of x is a function whose input x is a value which tangent takes, i.e., and now we gotta really erase a bit, which is in here, i.e., a ratio of y over x, where x comma y is a point on the unit circle. And I think this is the hardest one. Then the output is the unique angle theta such that, well, it turns out theta is again going to be between negative pi over 2 and pi over 2. So arctangent has the same range as does arcsine. And instead of sine theta is equal to x, we're going to have tan theta is equal to x. Okay, so for an example, we could do arctangent of, let's see if we did, why don't we do 1? Yeah, we'll do 1. Okay, so if we want to do arctangent of 1, what do we want? Well, we want to draw a unit circle. And graphically understanding arctangent is a little bit more subtle than understanding the other ones. So again, we're going to focus on the right half of the unit circle. And what is this 1? This is saying that the ratio y divided by x of the point x comma y is 1. The ratio of y divided by x should be 1. In other words, we want to put a point x comma y somewhere on this right half of this unit circle such that y over x is equal to 1. Well, if y over x is equal to 1, then I can multiply both sides by x, and we should get that y should be equal to x, right? If I divide y by x and I get 1, then those two numbers were equal. So I need to put a point here, this green point, should go somewhere on the unit circle, on the right half of the unit circle. And what should we have? We should have that the y value should be the same as the x value. If the y value should be the same as the x value, then that's telling me that this point should lie on the line y is equal to x. This is the line y is equal to x. So now I'm asking, well, which point on the unit circle is going to intersect this line? Well, it's going to be the point right here, where this is the point x comma y, and, well, y is also equal to x. Okay, so now the key for understanding the inverse tangent is to now draw, we want to understand what is this angle theta here. Well, it's a little bit tricky to understand this angle theta, but we can make it a lot easier by drawing in a triangle. And if we bring this triangle out, then what does it say? It says that we have a triangle. This side length here is 1, and this side length on the bottom is our x-coordinate. This side length on the side is our y-coordinate, but our y-coordinate is equal to our x-coordinate, so I'm just going to write x again. So I have a triangle here with a right angle inside, and two of the side lengths are the same. What kind of triangle has this property? there's a special triangle whose side lengths obey this property that two of them are the same, and it's a right triangle. That's right, Justin's got it. This must be a 45, 45, 90 triangle. So the angle in here is 45, and the angle in here is 45, and this angle is the one that we were worried about initially. We wanted to know what that angle is. So we found out that theta should be equal to 45 degrees, but we should express it in radians. In radians, that's pi over 4. So, in other words, arctan of 1 is equal to pi over 4. Okay, so never ever forget, we can always drop this line and make a triangle in here and use what we already know from geometry about 30, 60, 90 triangles, 45, 45, 90 triangles, and the Pythagorean theorem. We can use all that stuff to figure out what's going on inside the unit circle. Okay, so we've now covered all of arcsine, arccosine, and arctangent and done one example with each. How are we feeling about this stuff? Do we want to see more arc or like inverse trig stuff? Or should we move on to a new topic? It's up to you guys. It's your review. Okay, I'm not seeing anyone saying that they want to see more inverse trig. So did anyone come with anything else that they wanted to see some examples of or have a bit more explanation on? All right, if not, then I will go through some more questions. Okay. Here's a great question. I like this one. This one's fun. So let's focus on part A here. This is still kind of in the vein of inverse trig, but it's a little bit of a different kind of question. So the question says the following. It says, if sine of theta is equal to 0.7, we're supposed to know, well, in which quadrants can theta lie? Okay, in which quadrants can theta lie? Okay, so remember, if we have a unit circle, or if we just have a coordinate plane, we describe the quadrants in the following way. We call this quadrant 1, this quadrant 2, this quadrant 3, and this one in the bottom right is quadrant 4. Okay, and we're supposed to understand, well, in which quadrants can theta lie? Why don't I just move this drawing down here? Might as well be in the problem. Okay, so let's draw a unit circle. We're doing trig. I mean, it's never going to hurt us to draw a unit circle. Of course, that's more of like a unit octagon. There we go. Okay, and what does this part say? It says sine theta is equal to 0.7. So remember, the sine corresponds to the y values on the unit circle. So we're looking for to describe an angle theta such that the y value of the point which theta points at is going to be equal to 0.7. So what I'm going to do is draw in the line y is equal to 0.7. And what I'm looking for is the angles theta which point at this point. And there's two of them. There's this one, or there's also this green one. Okay, but the question isn't asking us to perform inverse trig. The question is asking us something that's more general. It's saying, if sine of theta is equal to 0.7, in which quadrants can theta lie? Well, it's okay for us to say that there's more than one in this case, okay, because we're not trying to actually make this a function. We're just trying to say something about these angles theta. And well, as we can see here, one angle theta points into quadrant 1, and one angle theta will point into quadrant 2. So the answer to this question would be quadrants 1 and 2. Or more accurately, it would probably be like 1 or 2. Those are the quadrants in which theta can lie. Okay, I like this question because it's it tests whether you understand like the geometric interpretation of the trig functions, right? The geometric interpretation is, well, if sine of theta is equal to 0.7, then we're talking about a point on the unit circle whose height is 0.7, and there are exactly two of them. And there are angles which point at those 2 points, and those angles have terminal sides which are in quadrant 1 and quadrant 2, respectively. Very nice problem. Okay, let's see another one. Let me add a page in here. Up here, I think. And we'll do maybe this problem. We're supposed to find the tangent of this angle. So what is our goal? Our goal is compute tangent of pi over 3. Let's remind ourselves how we do this. Well, first of all, the number one thing I want to do is draw a unit circle. I always do that. So I draw a unit circle, and inside my unit circle, I should draw the angle pi over 3. What is pi over 3 in terms of degrees? How many degrees is a pi over 3 angle? Good. 60 degrees, right? How do we get that? Well, we do pi over 3. We multiply by 180 over pi. The pi's cancel, and then we're left with 180 divided by 3, and 3 goes into 180 exactly 60 times. Okay, so what does a 60-degree angle look like? It looks like 2/3 of a 90-degree angle. So where is it? It's somewhere up here. And this is a 60-degree angle. Okay. And this is the point x comma y. And recall that the tangent is going to be the ratio y divided by x, where this y and x come from the point on the unit circle, which is given here. So in particular, I think we should try to figure out what the y value is and what the x value is. And there's something that I should do inside this unit circle. It's just begging for me to do it. What should I do now? I should draw something. How do I move forward here? Yeah, I should draw in a 90-degree angle to complete this triangle. Then this angle's 90 degrees. So tell me, what should this angle in here be? Good, 30 degrees. Okay, so let's bring this out so I can see it a little bit more clearly. I have a 60-degree angle here, and a 90-degree angle here, and a 30-degree angle here. And what am I interested in knowing? I want to know what are the coordinates of this point up here. Well, the x-coordinate, remember, the x-coordinate is going to describe, basically, is going to describe this distance here. Come on. The x-coordinate is going to describe this distance right here. And then the y-coordinate is going to describe the height, right? So the y-coordinate is going to then describe this height here. Okay, so I can fill in on my triangle here. I know that this length here is x and this length here is y. And now I'm really just going to focus in on this triangle and use properties of the 30, 60, 90 triangle to solve for what y and x are. Okay, and there's one more crucial piece of information that I'm going to need in order to finish this problem. Okay, so one more final inference that I need to make based on the fact that we are working on the unit circle. What else do I need to be able to know what is y and what is x? Very good, Justin. The radius is 1. If I have the unit circle here, and I draw from the inside of the circles to some point on the outside of the unit circle, this length is always 1, no matter where I draw it. Okay, this length here is 1, this blue length. This blue length here is 1, 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 and this blue length here is 1. And that's the side of our triangle. Has length 1. Now I can use the properties of the 30, 60, 90 triangle to understand what tangent's going to be. Well, I can immediately find out what x is going to be. Okay, x, the ratio between the length of the side which is across from the 30 versus the side which is across from the 90 is 1 to 2. Okay, in particular, the side here with x is half as long as the hypotenuse. So x is going to be equal to 1/2. And then the way we get the y side, okay, the y is across from the 60, is we take x and we multiply times the square root of 3. In our case, we get square root of 3/2. So what is this point here? We can fill in the coordinates now. X comma y is the point 1/2 comma square root 3/2. So finally, if we want to compute what is y over x, well, we just plug y in for y and x in for x, and we get square root 3/2. And then we divide that by 1/2. Dividing by 1/2 is the same as multiplying by the reciprocal of 1/2. So I'm gonna instead multiply times 2/1. The 2's cancel, and I'm left with the square root of 3. So tangent of pi over 3 is equal to the square root of 3. Okay, that's a review of how we use the tangent function. Okay, every single one of these trig problems, 9 times out of 10, it devolves into one of these special right triangle problems. Okay, so if you're not super comfortable with 30, 60, 90 triangles and 45, 45, 90 triangles, that is the #1 thing that I would study for the exam. I would go to YouTube, look up some Khan Academy videos on special right triangles, and practice problems where you have to find one side given the other side. Okay, or you have to find the angles given the side lengths. Okay, understanding special right triangles is 100% crucial for getting a good grade on the exam. So definitely make sure you study those. Okay, any questions about, oh, sorry, there is one. Set 1 equal to 2x to give you x equals to 1/2. Yeah, exactly. That's how you could do it. You could say, if this side length is x, right, then I know that the side length of the hypotenuse, which is 1, should be equal to twice the side length, which is across from the 30, which is x, and therefore x is equal to 1/2. Yes, you're exactly right, Sam. Okay. Any other questions about the tangent problem? Are there multiple rules for the 45, 45, 90 or the 30, 60, 90 with which all the sides will follow the same rule for each? No, there's same rule. So the rules are as follows. If you have a 45, 45, 90 triangle, then if this side length is x, then you know that the other side length is x, and you know that the hypotenuse is going to be x times the square root of 2. So in particular, if you want to get from one way to another, you multiply by the square root of 2 going in this direction, or if you're going in the other direction, then you divide by the square root of 2. And then if you have a 30, 60, 90 triangle, it looks a little bit more elongated. You have a 30 here, a 60 here, and a 90 here. Then the side length, which we call x, is the side length which is across from the 30. Then the way you get the side length, which is across from the 60, is you multiply by the square root of 3 to get x times the square root of 3. Or if you want to go the other direction and go from the side length, which was across from the 60, and go to the side length, which is across from the 30, then you should divide by the square root of 3. If you want to go from the side length, which is across from the 30 to the side length, which is across from the 90, then you multiply by 2 to get 2x. So this is a multiply by 2. And if you want to go the other direction, then you should divide by 2. And if you want to go from this side to this side, well, what should we do? We have an extra square root 3 that we want to get rid of, and we want to pick up a 2. So we multiply by 2 divided by the square root of 3. And if we want to go the other direction, from the hypotenuse to the side length across from the 60, we should multiply by the square root of 3 and get rid of the 2. So these are the rules of how we navigate these special right triangles. Okay, in our case, if we're on the unit circle, you can even simplify this. You know every single time that a 45, 45, 90 triangle has the following dimensions: square root 2 over 2, square root 2 over 2, and 1. 1 is always on the hypotenuse for our triangles in the unit circle. And a 30, 60, 90 triangle looks like this. 1, again, on the hypotenuse. Across from the 60 is square root 3 over 2. And across from the 30 is 1 over 2. But don't be confused, because there's two orientations we might see this 30, 60, 90 triangle in. Sometimes we see it more like this one. Okay? What you got to remember is that across from the 30, that's where the 1/2 goes. Across from the 60, that's where the root 3 over 2 goes. And across from the 90 is where the 1 goes. Okay, so these are just for the unit circle. Okay. Yeah, I would guess that if you thought that there was another case, it's probably because there's a slight difference between these two 30, 60, 90 triangles, depending on where the 30 is. You know, it's going to depend. Also, sometimes we know the side lengths and we need to say what the angles are on the inside. So if you see a triangle which has these side lengths like this, and you're asked to find out, well, what is this angle here? Well, you say, this looks like a 30, 60, 90 triangle. I can tell because of the ratios of these side lengths. And I know that the ratios of the side lengths is telling me that this is a 30, 60, 90, and I know that this one would be 30 because this side length is half of the hypotenuse. And therefore, this side length has to be, or this angle has to be 60 since it's across from square root 3 times the side, which is across from the 30. Okay. So that's it for today. I mean, we're done with the review. What I'm going to do now is sit in here for the following 2 hours and 10 minutes, and I'm just going to keep going. So if you feel like sticking around and having some more review, please do. Otherwise, you're not required to be here even just for the regular lecture, so you're free to go if you wish. Otherwise, I'm just going to carry on with this review for as long as office hours go. So if you have questions, don't forget you can. Yeah, the review will be recorded, and I'm going to record the entire 3 hours, so it'll be on YouTube later today as soon as I'm done recording it. I'll put it up, and you guys can watch it later if you want, or you can stick around right now and see more math. Okay. So, does anybody have any further questions that they wanted to ask before I just kind of go and do some more general review? Okay, seems like not. Here's a good question. Find the length of the arc on the unit circle, which is defined by the given angle. Okay, so we have some angles here, and we're supposed to find out, well, what is the angle measurement? What arc length does the angle measurement produce? So let's try pi radians. So first of all, if we want to talk about arc length, we should probably have an understanding of the unit circle. And in particular, what we should understand about the unit circle is what is its circumference. So if I were to stand here on top of the unit circle and walk all the way around back to where I was, this distance is 2 pi times the radius of the unit circle. The radius of the unit circle is 1, so this is 2 pi. So if I want to know how long is it for me to walk from, and really I should have started, if I was being really good, what I would have done is started here and walk in this direction like this, back to where I was. That's 2 pi. So if I want to understand, well, how long does it take me instead to walk not all the way around the unit circle, but just until I'm facing pi radians? Well, I'm interested in knowing what is this arc length of this green part of the unit circle, because this is where the pi is. So I want to eventually end up facing over here. So eventually I'll be facing in this direction. And I want to know, well, how far did I walk to get over there? Well, it's not too hard to see that I walked halfway around the unit circle. And I know that all the way around the unit circle is 2 pi. So if I want to know what the arc length is, I can just take 2 pi divided by 2, and I get pi. So that's one of the amazing things about radians, is if you have an arc length on the unit circle, which is defined by an angle measurement, which is in radians, then x radians gives us an arc length of x. So these questions are really easy to answer. If we want to know what is the arc length of the arc on the unit circle defined by the given angle, for pi, it's just pi. For 2, it's just 2. And for 1.7, it's just 1.7. It's that simple. And that comes from the definition of what a radian is. It was defined in order to satisfy this property that pi radians gives us an arc length of pi. Okay, so that's a fun question. Let's move on to something a little bit more substantial, maybe. We're not going to worry too much about arc length. Here we go. This is a fun review that you can do. Well, we want to find the indicated points. Okay, and in fact, we can do them all just by finding these 3 points and then using the symmetry, right? Because the way we get, if this is the point x comma y, and then we just reflect about the y-axis, then this will be the point negative x comma y. So as long as we know what these 3 points are in the first quadrant, we're going to be able to fill out the entire rest of the unit circle. So this can be done in the following way. Well, if we put this triangle here, then what do we get? Well, this is 1/3 of a 90-degree angle, so it's a 30-degree angle. This is a 60-degree angle, and therefore this point x comma y has the values which are going to correspond to the length of this triangle. Well, the hypotenuse is 1. We just talked about this triangle. It's got side length 1/2 across from the 30 and side length √3/2 across from the 60. So this is the point whose x value is √3/2 and whose y value is 1/2. Okay, then if we draw in this triangle, then its length here is 1, and I know that this angle here is 45, and I know then that since this is a 90-degree angle, this should also be a 45-degree angle, and the side lengths of this angle are √2/2. Sorry, side lengths of this triangle are √2/2. So then this is the point √2/2. √2/2. And then the last one here, well, we've got now the 30-degree angle is in another place. The 60-degree angle is down here. So we get √3/2 on this side and 1/2 on this side. And then this is the point 1/2 comma √3/2. So then to find out, well, what are all of the other points which are on this unit circle? It's not too hard. All we have to do is copy these points over with the appropriate reflection. So let's start up here. This point Well, the x value is going to come from the x value of this point, except it's going to be negative now. So it's going to be negative 1/2, and the height is the same, √3/2. This point here, same deal, negative √2/2, keep the height the same. This point here, we take the blue point now, and we copy it across. We get negative √3/2, 1/2. And the other points we get similarly. This one will be negative √3/2, negative 1/2. This one will be negative √2/2, negative √2/2. This one will be negative 1/2, comma, negative √3/2. This one will be 1/2, negative √3/2. This one will be √2/2, negative √2/2. And this one will be √3/2, comma, negative 1/2. So as long as we know how these triangles fit in the first quadrant, well, the way we figure out how they fit in the other 4 quadrants is the same. The only thing we have to do is reflect, which means we multiply one of our coordinates by -1. Okay, so that's how we can figure this one out. It's not too hard. By the way, having something like this handy on the exam will really help you, because then you can just, look at your problem, and if your problem looks something like, a unit circle with a thing in here, well, you just find the triangle which looks like the one that you want, and then you can just get this point automatically from this graph. So that's one nice thing you can do. Okay. We can try this one. Looks like we've got 4 graphs here. And we're supposed to do the following. We're supposed to determine whether these graphs are graphs of periodic functions. If so, identify the corresponding period and amplitude. Okay. So let me ask you guys, I want you guys to prepare in the chat, but don't put enter yet, but prepare whether you think, I want you to give me the list of A, B, C, and D, which of these functions that you think are periodic. So include all of the ones that you think are periodic and none of the ones that you think aren't periodic. Okay, but don't hit enter just yet. I want you guys to think about it for 30 seconds and then give me your answers. All right, let's see them. What do we got? Between A, B, C, and D, what do we think? Which ones of these do we think are going to be periodic? Okay, bit of a disagreement on B. So B is a question mark. I think A, we both agree on, right? I think A is going to be periodic. I mean, A looks like sine x. And we know sine x is periodic, right? Okay, so A is definitely periodic. For whichever one of you said that B is maybe not periodic, can you give a reason why you think that B might not be periodic? I think it was Mitchell. Mitchell says B is not periodic. Can you give me an explanation as to why? Okay, don't know exactly, just remember going over the graphs. That's fine. Okay, but what's different between B and A? There's a pretty big difference. The difference is, well, A has the property that the height of every single wave is the same, right? And B has this kind of crazy thing where we go up a little bit, and then the next time we go up more, and then the next time we go up more, and so on and so forth, right? So the definition of periodicity said the following. It should say that f of x is equal to f of x plus a for some a and every x, meaning that the height of the function at a given point is the same as the height of the function at some later time in some perfectly repeating way. Okay? In other words, for the sine x function, what I can do is I can take a point here and I can say, well, if I move 2 pi units to the left, then the height of this point will be exactly the same as that point. Okay? And this is true for this graph as long as you choose x to be 0, then, well, the zeros repeat on a very kind of periodic basis, right? So you might say, well, maybe this thing is periodic and the period goes from, the period goes from here to here. But the problem is then, if we take that same length and move it to be from here to here, then the height of our points is not the same. Okay, so this is the reason why this one is not periodic, is the height, the function values are not repeating. There is a function value, which is repeating, but for it to be periodic, we need it to happen for every single point. So no matter which point we choose, we can move over 2 pi units to the right. And guess what? The height of the point later on is going to be exactly the same as what it was before, right? We can take any of these points and just move them over, and we're going to get the same thing. Okay? It's true for the 0 here, but it's not true if I move this point over. Well, this point is not a point on the graph of our function, so it's not periodic. So that's why B is not periodic. If we take this same, principle and apply it to C, it's not hard to see that C is also going to be periodic. We take any point and we move it over a certain amount, we get a point which has the same height as before. Okay? Or if we do it over here, that's fine too. So this is, yes, periodic. And this D one is a little bit tricky. Want to check D? Well, what do we want to check? Again, we want to check, is there some recurring basis upon which if I move a point over a certain amount, then the function height is always the same. So if I use this same distance here on any point which is down on the bottom, well, it would look like this. And again, I get the same function value. Okay, so it turns out that this function actually is periodic. Okay, and if we pick any distance, which is a certain amount apart, then the function value is going to be the same. Okay, which is the definition of periodicity. Okay, so a periodic function doesn't necessarily have to look like a wave. Yeah, equal movements and heights, pretty much, Mitchell. That's the gist of it. Okay, so let me erase all this jazz that I drew on these things. And let's see if we can figure out what is the period of all of these functions. Well, the period, remember, should be the distance from crest to crest of our wave. In other words, it's the distance upon which the function is always repeating. So we don't need to worry about b because b is not periodic. But in this case, the period is going to be this distance here, which if we move it down, we can maybe see a little bit more clearly. Should go from here to here. And this looks like roughly 3 and negative 3. This is actually the graph of sine, so I'm just going to say period 2 pi. Now, how do I find out what the amplitude of a periodic function is? What is the amplitude of a periodic function? Yeah, so 6, roughly 2 pi. 2 times 3.14 is like 6.28, so pretty close. I think 6 would be a perfectly acceptable answer for this period. How do I see the amplitude, though? Amplitude would be 1, right? It's this distance, which in our case is 1. So amplitude 1. Okay, so let's try the next one. We'll try C, because C was the next periodic function. Well, we want to know what is the distance before we repeat our value, right? In this case, we could move it down onto the x-axis in the following way. It goes from here to here, right? Yeah, 3, or this is actually the graph of tangent of x, so it's actually pi, which is roughly 3 for the period. And then for the amplitude, what do we think the amplitude of this one is? What do we think the amplitude is? Remember, the amplitude is going to tell us how high our wave is, right? That's what we don't know, right? Well, if we look at tangent, remember tangent has this kind of vertical asymptote here. And it just goes up and up and up forever, and then down and down and down forever, right, in both directions. So if I want to describe what is the maximum height of a point in each subinterval, what would you say? The maximum height of points which are in a subinterval. Yeah, very good. I think infinity is probably the best answer we could give here. I would say amplitude, infinity, or undefined. All right, how about D? What do we think the period is for D here? For D. Sorry, not for D. Sorry. So the period, remember, the period is describing how far between points that repeat. So it's a horizontal distance somehow. Two, okay. So this is an interesting premise. So the thought is maybe, well, this is the repeating scale, right? So we just have two. But we need to have the following. Okay, we should have that f of x is equal to f of x plus 2 for all x. What happens if I choose this to be my original x value? Then x plus 2 will be somewhere here. And now the height of my function is all the way down here. Yeah, I think we should do 4, right? Because 4, if I go over x plus 4, then I'm again sort of in the middle segment of that part there. You see what I mean? Yeah, so I think we should use 4. Okay, and then if I consider one region, which one repetition is basically we go up and then we go down and then we're back to where we started, right? What is the maximum height or the maximum depth in these regions? 1 again, right? It's 1. That's the amplitude. Okay, so that's how we find out the amplitude of this stuff. Okay, and period. Any questions about the periodicity or the period or the amplitude? Okay, looking pretty easy. Then we'll move on to something harder. Do you want to, you're the last one, so do you want to maybe have something specific you want to work on?
Dentist, but I have to go. Yeah.
Or want me to just kind of find something for us to work on? Good, just going with the flow. Okay, cool. Then I'll find something else, maybe something a little harder. Okay, we can try this problem. We don't even need to use a calculator for this. Our goal is to find out, well, what is sine squared theta plus cosine squared theta when theta is equal to 0? Okay, so we could find this out in the following way. We could draw the angle 0.
Know if they're all if these are all the process are in place, but these are the things the process they would use.
Let me ask you, which direction does the angle 0 face? Directly to the right, good. So here's 0. So the point on the unit circle, which we're going to refer to, is going to be this point. What are its coordinates?
Okay.
Okay, so remember, the first coordinate is going to describe how far left and right we go. And the second coordinate is going to describe how far up and down we go from the origin. So we move from the origin, we go to the right a certain amount and up and down a certain amount. So how far left and right do we go on the unit circle to get from this point over to this one? Okay, we go right, so, and we don't go up and down at all, so this one should be 0. But what is the length? Oops. What is this length, which I'm going to draw here in blue? Yeah, 1. The radius of the unit circle is 1. Okay, so this is the point 1, 0. So which one of these is cosine theta and which one of these is sine theta? That's right. Cosine theta is 1 and sine theta is 0. So if I want to do what is sine squared of 0 plus cosine squared of 0, we already found out that cosine of 0 is 1 and sine of 0 is 0. So this is going to be equal to 0 squared plus 1 squared is equal to 1. So we got 1 in here. Okay. Okay, so let's try pi over 3 now. Draw a unit circle. What kind of angle is pi over 3? What does it look like?
Hi.
Maybe it would help to convert it to degrees. You know how to convert an angle measurement from radians to degrees? Yeah, I mean, we want to multiply by one of those. My question is, should we multiply by 180 over pi, or should we multiply by pi over 180? Which one should we do? I want you to tell me so that you feel confident in your answer. Yeah, 180 over pi, right? Because that's the one that's going to cancel the pi. So we get 180 over 3, which is 60 degrees. Okay. So you tell me, between the three angles which I'm about to draw, the green, the blue, or the purple, which one is 60 degrees? Yeah, we're going to have a 30, 60, 90. But first I want to just draw the angle inside here. I want to draw pi over 3. I know it's 60 degrees. So which of the three angles that I've drawn here are 60 degrees? Okay, green. Let's think a little bit here. Do you know what a 90-degree angle looks like? If I was going to draw another red line somewhere here, that would make this angle between the two red lines a 90-degree angle. Well, right, but let's not focus on the triangles just yet. We're getting a little ahead of ourselves. We're just trying to draw the angle here. Where should I put this red thing in order to make the angle between the two red lines 90 degrees? Oops. Where should I put this in order to make a 90-degree angle? On the y-axis. Then this would be 90 degrees, right? Okay, so this would be 90 degrees. So what would this orange angle be then? I'll give you a hint. This orange angle cuts the 90-degree angle in half. So this should be a 45-degree angle, right? So then if this green one is even smaller than that, what do we think the green angle should be? 30-degree angle, that's right. And how about the purple one? That's right, 60. Okay, so here's what I want you to remember. I want you to remember how to recognize whether an angle is a 30-degree angle or a 45-degree angle or a 60-degree angle just by looking at it. Okay? The way you do that is by checking, well, does it look like exactly half of a 90-degree angle? Okay? In other words, if I put two of that angle back to back, would I get 90 degrees? If so, then it's a 45-degree angle. If it's less than that, then it might be a 30-degree angle. The way you can check if it's a 30-degree angle is, well, if I did three of these back to back to back, whoops, not there. If I did three of these back to back to back, would I get a 90-degree angle? Okay. And then a 60-degree angle looks like, well, more than a 45-degree angle, right? Yeah, I think you got a little ahead of yourself. That's true. Okay, so let's try to figure out what the heck we were doing before. We're trying to put a 60-degree angle in here so that we could figure out what the value of sine and cosine of this angle would be. So I'm going to draw in now the angle pi over 3, which looks like a 60-degree angle. So it should go up here. And then this angle here is a 60-degree angle. Now you tell me, what should I do now in order to find out what the points x comma y are? That's right. I think that's a good idea. So we should put a 1 on the radius. And then we should draw in a dotted line to complete a triangle. And remember, our dotted line will always be a vertical line. So then we get a 90-degree angle here. So the last one should be a 30-degree angle. So the next question is, what are the side lengths of the triangle, right? What's the side length which is across from the 30 going to be? This one in green. Not square root 2 over 2. Square root 2 over 2, remember, goes with the 45, 45, 90 triangle. And we've got a 30, 60, 90 triangle. Want to adjust your answer? Square root 3 over 2? Let's take a look at our triangle. We've got a 30, 60, 90 triangle. I want to know which side is across from the 30. This should be the smallest one. There we go, 1/2. Trial and error. Okay, I really think you should spend some time reviewing special right triangles, because I think there's a common theme in the class that there's a lot of students who don't have as good of an understanding of special right triangles as would really kind of be required to do well on the exam. So you should definitely study the 30, 60, 90 triangle and the 45, 45, 90 triangle. Okay, so which side, what should the side length be which is across from the 60 now? There we go, square root 3 over 2. So what are the coordinates of the point x comma y? Good. 1/2 square root 3 over 2. Those are the coordinates of this point. Now, which one's cosine and which one's sine? Good. This is cosine of an angle. What's the angle that this is cosine of? This is sine of an angle. What should go in these parentheses here? The angles. Yeah, which angles? Not quite. These are the angle which should go in here is just this angle, which is inside of our unit circle. Okay, so these are actually both cosine of pi over 3 and sine of pi over 3. Same angle, okay? So if you're asked to find out what is sine of pi over 3, what you would do is you would put the angle 60 in here, you would find the coordinates of this point, and then you would check, well, which one is the y coordinate? It's square root 3 over 2. Okay, and if you're asked to find cosine of pi over 3, you do the same thing. You draw the same triangle, get the side lengths again, except the answer would then be the x coordinate of that point. So the angle is the same. We're just talking about different coordinates of the same point. Okay, so then what do I do if I want to know, what am I trying to do? I'm trying to find sine squared theta plus cosine squared theta. Should have been pi over 3. Now what do? I want to find out what this is. It is actually one of the identities, but how could I figure it out if I didn't know the identity? I'll give you a hint. It has to do with the thing that we just found out. What did we just do all that work to find? We found out what the coordinates were of this point. So we know what cosine of pi over 3 is, and we know what sine of pi over 3 is as well. What then can I do? Yeah, plug them in. So root 3 over 2 goes in here, and then I square it. And then I do 1/2, and I square it. And I get 3 over 4 plus 1 over 4 is equal to 4 over 4 is equal to 1. So we got, again, sine squared theta plus cosine squared theta is equal to 1. And at this point, we might be getting kind of suspicious about this problem. And I think you're right. We may have had an identity about sine squared theta and cosine squared theta. Do you remember what it was? If we add them together? Well, we had some options for rewriting these, but we had a Pythagorean identity. The Pythagorean identity said what? Bam, there it is. Sine squared x plus cosine squared x is equal to 1. Regardless of what x is. Okay? So if we want to know what is sine squared theta plus cosine squared theta, it's just going to be equal to 1. And it doesn't matter what the angle is 1 and 1 again. In fact, if I look at the next one, what is the angle here? Theta plus 1. And the angle here, theta plus 1. So sine squared theta of theta plus 1 plus cosine squared theta of theta plus 1, what do we think we're going to get in these 3 blanks? Or these 4 blanks? Three. How do we get 3? Just adding 2. Well, remember, we said that this angle theta here could be anything it wants to be, right? As long as it's the same angle in each thing, then it's going to be true. We found out that theta, sine of square root of 0 plus cosine square root of 0 is 1, sine square root of pi over 3 plus cosine square root of pi over 3 is 1, sine square root of pi over 4 plus cosine square root of pi over 5 pi over 4 is 1. So if we just add 1 to all those angles, then this will just be, like the same thing as if we had done 0 plus 1 and then pi over 3 plus 1 or 5 pi over 4 plus 1 into this same equation. So based on that, what do we think we might get in here? Yeah, 1 again, across the board. Sine squared of some angle plus cosine squared of the same angle is always equal to 1. That's what this identity says, right? It doesn't specify what theta actually is. Theta could be theta, or theta could be theta plus 1, or theta could be even negative 5 theta. So guess what? Again, in the bottom row, it's all 1s. So this is one problem where understanding this identity could have saved us an awful lot of time. We would have never even started drawing unit circles and computing cosine and sine and then trying to plug them into this formula and squaring them and adding them and getting 1 if we just understood that this formula means that if I do sine squared theta plus cosine squared theta, it doesn't matter what theta is, it's always 1. And why is this true? Well, it's true because basically the following. If I draw a triangle in here, then what do we have? Crap, maybe I could. Oh, wait, how can I do this? Crap, I can't do that. Okay, well, if I draw a triangle in here, it doesn't matter where I draw the triangle. There's going to be a certain property which is true every single time. Remember, the cosine of theta is this value here, of this side length, and sine theta is this value here. Or if I have some other angle here, which is, I don't know, call this angle beta, then this side length is sine beta, and this side length is cosine beta, right? So what's always going to be true is that the sides of this triangle obey the so-called Pythagorean theorem, right? If I have the sides of a triangle, then the side length, the sum of the side lengths squared is always going to be the length of the hypotenuse. And no matter where I draw a triangle in this whole unit circle, the hypotenuse always has length 1, right? So that's why if I do sine squared of theta plus cosine squared of theta, it's like taking the sides of a triangle, squaring them, and adding them up. What do we get? The square of the side length of the other side of the triangle, which is 1. So it doesn't matter what the angle is. If it's the same angle, then sine squared theta plus cosine squared theta is always going to be equal to 1 because it has to be that way. It's a triangle. Okay, does that make sense? Okay, cool. All right, how about sketching graphs? Oh, you have class at 10:30. Okay, you want to call it there then? Or do a little more? Will I finish out going over them and record it? Sure, I'll I mean, I'll do what I can for the next little while anyway. Yeah, I'll go until the end of office hours, so I may not be able to finish this entire thing, but yeah, I'll go over more and I'll post it on the YouTube and you can check the review. Yeah, no problem. All right, cool. All right, for those of you that are watching the recording, I'm gonna take a 5 to 10 minute break and then I'll be back and then I'll try to go through even more of this. So I'm gonna leave the recording going, but I will be right back. Okay, I'm back. So I'm going to keep going through this review section for anybody who wants to watch the recording. Probably go for like another hour or so. So I'm going to start in on 5.3 here, and I'm just going to, oops, tab page here. I'm just going to do the following. So I'm going to try to sketch the graphs of sine theta and cosine theta. So one could pretty easily do this from memory, but I'm going to do it as though I've never memorized what these graphs look like. So what am I going to do? Well, I'm going to draw a unit circle. And I'm going to evaluate sine and cosine for various different angles, theta. So first, if theta equals 0, then we're pointing directly at this point to the right. Okay, so terminal side is the same as the initial side. And this point in Euclidean space, just, if I wanted to look at like a, Euclidean space as in, like this, right? When we have dashes on the thing, and then we just say, well, how far left and right do we go? How far up and down do we go? Well, we go exactly 1 unit to the right and no units up and down. So this is the point 1, 0. Then when theta is equal to pi over 2, the point here is the point 0, 1. Then when theta is equal to 3 pi, we get the point -1, 0. And then finally, when theta is equal to 3 pi over 2, we get the point 0, -1. And then when we're at 2 pi, our point is gonna overlap, right? So theta equals 2 pi, we get, again, the same point, 1, 0. And then everything's going to repeat after that. Okay, so the key here is to recognize, well, remember, cosine of theta is going to represent the x-coordinate of one of these points. So cosine of 0, cosine of 0 is 1, and sine of 0 is 0. And then up here we have cosine of pi over 2 is equal to 0, and sine of pi over 2 is equal to 1. And so on and so forth. So what is happening to the y values? Well, we want to know what's happening with sine. So sine starts at 0, and then we go up to 1, and then we go to 0, and then we go to -1, and then we go back to 0, and we repeat. So those are the points which I'm going to graph on the sine function. When theta is equal to 0, okay, remember theta is on this axis, okay, so I'll make my markings here. Theta is 0 here, it's pi over 2 here, it's pi here, it's 3 pi over 2 here, and 2 pi here. So I can check, well, what does the graph of this thing look like? Well, it takes value 0 at 0, it takes value 1 at pi over 2, it takes value 0 at pi, it takes value -1 at 3 pi over 2, and it takes value 0 again at 2 pi. And I know these graphs look kind of squiggly, so I'm just going to connect all these points by some squigglies. And this is the basis of the sine graph. And from here on, all I'm going to do is I'm just going to replicate this over and over again in both directions. So going the other way, we would go down 1, and then up 1, and then up 1, and then down 1, and then so on and so forth. Dot, dot, dot. Carry on. And then on the right side, what we're going to do is we're going to go up and then down, and then, so on and so forth. Dot, dot, dot. So here's sine theta, where y is equal to sine theta. Okay, so that's what the sine graph looks like. You can figure it out just by checking out what are the y values of these points. And now I'm going to use a different highlighter color. I'm going to use the red highlighter to check what's happening with the cosine. Well, cosine is the x value. So when theta is 0, cosine's 1. When theta is pi over 2, cosine's 0. When theta is pi, cosine is -1. When theta is 3 pi over 2, cosine is 0. And I'm just going to plot those points in that order. So again, pi over 2, pi, 3 pi over 2, 2 pi. What do these points look like? Well, at 0, we're at 1. At pi over 2, we went to 0. At pi, we went to -1. At 3 pi over 2, we're back at 0. And at 2 pi, we're back at 1. So what does it look like? It looks like this bell shape thing. Okay, and to draw the rest of the graph, I know that this function is 2 pi periodic. So all I'm going to do is I'm going to exactly copy what's in here, and I'm just going to paste it over and over again elsewhere. Right, same deal on the right-hand side. What does it look like? Well, we just keep doing that. Okay, so that's the cosine function. So these two functions look a little bit different. Remember, cosine is always starting at 1, and it's even, meaning that if we reflect a point about the y-axis here, it kind of goes across, directly across. Whereas, so this is saying that cosine is even. In other words, cosine of theta is equal to cosine of negative theta. Sine, on the other hand, is odd, meaning that if we take a point here, the way we find the point on the other side is we reflect through the origin. So this is telling us that sine of theta is odd. In other words, sine of x is equal to sine of negative x. Negative sine of negative x. Okay, so this is how we do the graphs of sine and theta, or sine and cosine. The way we get the graph of tangent is just by taking, for each x value, we take the y value of sine theta and we divide it by the y value of cosine theta. Okay, forget about this question. What is the amplitude of sine theta? Well, the amplitude of sine theta is going to be the height of each wave. So the amplitude is going to be 1, and the amplitude of cosine theta is again going to be the same thing. It's going to be 1, right? We can see this up here. It's this length here is the amplitude. It's the height of each wave above sea level. So we get 1. Now, what is the period? Well, the period, remember, is going to be the distance from crest to crest, which in our case goes from pi over 2 to 2 pi plus pi over 2. So if we take this distance here, this will be the period. And that's going to be equal to 2 pi over 2 pi plus pi over 2 minus pi over 2, which is just 2 pi. So the period of the sine function is 2 pi, and it's also the period of the cosine function. What would their periods be if we were measuring angles in degrees rather than radians? Well, that's not too hard. We just say, well, we just need to convert 2 pi radians into degrees. Well, we just multiply by 180 and divide by pi, and we get 360 degrees. Right, because we cancel the pi's, and then 2 times 180 is 360. Okay, and then for the domain and range of sine theta and cosine theta, well, the domain is all the angles theta, which if we put them inside the unit circle, they point at some point on the unit circle. Well, it doesn't matter. We can choose any angle we want. We can choose angle 1 billion, or we could choose angle negative a billion, or we could choose angle 0.000001, right? There's no angles which are going to be able to escape the unit circle because of the direction that they're facing, right? It's kind of surrounded on all sides. So all angles are permissible. So domain is all real numbers for both. And then the range, well, the range of the sine and cosine functions are going to be the possible y values which are taken by the graph. Well, if we consider all possible y values such that if I were to, put a line here, then it would intersect the graph at some point somewhere. Well, the only y values where that's not going to happen is if we're too high, right, or too low. If we're too high, like up here, then this line is just going to float above our graph forever. So likewise, if we're too low, then this line here is going to float below our graph forever and it's never going to touch it. But if our line here has height anywhere between -1 and 1, then we're going to be able to touch points of this graph using this horizontal line. So that was how we defined the range back in the day. And the range for both of these is again going to be the same. It's from -1 to 1 inclusive, right? Because that 1 is actually achieved at the points, well, for cosine, it's at the point theta equals 0. Then cosine is actually equal to 1. And for sine, it's when theta is pi over 2. Okay, so that's how we find the range and the domain of sine and cosine. Okay, so now we have a sort of nasty looking function. Problem 2 here. We're supposed to consider what is the generalized cosine function g of x equals a times cosine of b of x minus h plus k. Okay, so this is kind of annoying. What does it basically say? It says ultimately that we have a vertical stretch by a horizontal compression by b. We have a where'd it go? We have a vertical shift by k, and we have a horizontal shift by b times h, because we would distribute this on the inside. So let's do that. We would get a times cosine of bx minus bh plus k. So the transformations are vertical stretch by a, horizontal compression by b, horizontal shift by b times h, vertical shift by k. So we want to know what is the period. We're going to forget about the midline. And then what is the amplitude? Okay, well, the period is not really going to be affected by a horizontal shift or by a vertical shift. Likewise, the amplitude is not going to be affected by a horizontal shift or a vertical shift. Here's how you can see that. If I have a function here, say I have, I don't know, some sine-looking function. Well, if I want to look at the period, which is the distance from crest to crest, or if I want to look at the amplitude, right, which is the distance from the x-axis to the top of our wave. Well, if I move this whole system left and right, then these distances are not changing. Likewise, if I move these distances up and down, if I move this thing up and down, these distances are not changing. Okay? So these distances are not changing under vertical and horizontal shifts. So we can forget about h and forget about k because we're only asked to say something about the period of g and the amplitude of g. Okay? So here's how this is going to work. Well, the period of g is saying something about left and right distances, right? It's the distance from crest to crest. So if I take this whole thing and I squeeze it in by a horizontal compression, then this green distance is also going to get squeezed, right? It's also going to get squeezed. So however much the horizontal compression is, which in our case it's B, it's also going to compress the period. So if the period of cosine is 2 pi, and then we compress horizontally by B, then the period, the new period, is 2 pi divided by B. Okay, that's a horizontal distance that we have, compressed. And then this A here, well, the amplitude of g of x is going to get stretched, right? If we take this whole thing and we stretch it up and down, right? Like I don't know, a piece of gum or something, or a slinky maybe, stretch it up and down. Then what happens? Well, what happens if I stretch up and down is the amplitude is also going to be stretched up and down, right? This orange distance, which goes from the x-axis up to our point, is then going to get stretched up. Same deal with the graph. So it's also going to be stretched by a factor of A. So if I want to know the amplitude of g of x, I just need to know what is the amplitude of cosine. Okay, amplitude of cosine is 1. And then we stretch by A. This tells us that the new amplitude is A. Okay, so that is how we do this problem. So kind of a very general thing here that we're working with. We don't actually know what A and B and H and K are, but we know how to handle what's going to happen to their period and what's going to happen to their amplitude, okay, by just checking, well, which one is affected by a horizontal stretch? Well, horizontal distances are affected by horizontal stretches, and therefore the period is going to be affected by this B here, and the amplitude A is going to be affected by a vertical stretch, right? Because it's a vertical distance. It's a vertical measurement. So if we stretch things vertically, it's going to change. Okay, so that's another problem. God, this is hideous. What does it look like? It looks like I think this is like a 0.9. So this looks like a 0.5. So roughly, all right. So we're supposed to come up with an equation for this graph. I don't love this problem because it's a little bit annoying, but let's see. It looks like we've been shifted up. We've taken a sine function, which we've shifted up. This is our new kind of basis here. So we've moved everything up by 1. And then let's check now, what is the amplitude? Well, the amplitude is this distance, which can be seen right here. Right? Looks like it's 1, 2, 3, 4 units. So our amplitude is 4, which means we had a vertical stretch by 4. Also, the sine function usually goes straight up, but in this case it's going straight down, which means that we have had a y-axis reflection, not a y-axis, as x-axis reflection. phone's getting blown up. Okay, x-axis reflection. Maybe I should have drawn that in a different color. Why don't I make that an x-axis reflection in brown? So that means that everything that was up is, or was down before, I guess, now kind of came up, right? So these are the transformations we have. We have one more transformation, which I think is going to be a horizontal compression. It looks like everything's kind of been moved inwards. To check how much, well, we can check what is the distance from crest to crest. That would give us the period. This distance from crest to crest here, if we move it down onto the x-axis, goes from, looks like 1.5 to about, what is this? So this is 2, 3, 4. So it goes from 1.5 to 3.5, which means that this distance here, from 1.5 to 3.5, is exactly 2. Or roughly 2, maybe. So roughly 2, that's making me think like the period went from 2 pi to roughly 2, which means that the period, we can solve, the period got divided by pi, basically. So we can think of that as a horizontal compression by pi-ish. No, it's not that important. Pi-ish. Okay, so if I want to get everything into one, how do I do it? Well, I start with a sine function. I've got a vertical stretch by 4, so I put a 4 out front. I've got an x-axis reflection, so I make it negative. I've got a up by 1 shift, that means a +1 out back. I've got a horizontal compression by pi, so the horizontal compression is a pi here times x. And then I also need to, no, that's it. I don't need it. I don't have any other stuff. So why don't I move this over? Okay, so that is how I write the formula for this graph using sine. A little bit of a tricky problem. But not too bad. All right, 1 second. Okay. Marathon review. All right, so the next one is, okay, we're supposed to write a formula for the graph above using cosine. So rather than doing this whole thing over again, I'm just going to remember the following. Fact says cosine of, well, sine of x is equal to cosine of x. If I move cosine to the right, that would be a minus pi over 2. Okay. And this is also telling me that -4 sine of pi times x plus 1 is going to be equal to -4 cosine of pi, but I'm going to replace x by x minus pi over 2. X minus pi over 2. And then I get a plus 1 out back still. So then this is my answer for this cosine formula for this graph. Just came from this fact that a cosine function is really just a sine function moved over a little bit. So if I take our function and I move it over a little bit, then I'm going to get a cosine function. Okay, so that's where these facts came from. I just replaced x by x minus pi over 2 and changed the sign to a cosine. Same deal here. I had an x. I replaced it by x minus pi over 2. Okay. All right, word problem time. The electric current flowing through a circuit in milliamperes, at a time t is given by the equation I of t is equal to 400 times cosine of 4 pi t plus 2 pi. So some kind of periodic current, which is at times more current is flowing and at times less current is flowing. And it's on some kind of periodic basis. Okay, so find the amplitude, period, phase shift, and horizontal shift of the graph of I of t. Well, it's not too hard to find out. We have a vertical shift by 400. Phase shift by 2 pi. Horizontal shift. No, horizontal. Oh, I said shift before. I meant to say stretch. Vertical stretch. We have a horizontal, not stretch, but compression. By 4 pi. All right, so that's what it looks like. Okay, and we're supposed to sketch a graph of the function over one period. Well, if we compress the period of 2 pi by 4 pi, we get 2 pi over 4 is equal to 1/2. So that's the new period. So it's a cosine function with period 1/2. So it's going to look something like start at 400, right? Because the cosine function, oh wait, we've also got a phase shift by 2 pi. Well, phase shift by 2 pi is going to not change anything, since the period of our original function was 2 pi anyway. So it's going to look something like this. No, what? Something like this. God, it's a really skinny graph. Something like this, and then so on and so forth on the other side. Oh, we were only supposed to do it over one period, so great, we did it. So the period is 1/2. The amplitude is 400. And the phase shift, although we did phase shift by 2 pi, phase shifting a 2 pi periodic function by 2 pi is basically, we're going to get the same exact thing. Because if you think about it, if we have a cosine function, right? What does it look like? It's essentially saying if we take this whole thing and we move it over far enough, well, it looks exactly the same as it did before. Okay, if we move it over far enough, it looks exactly the same as it did before. That's what it means for a function to be periodic. In fact, I could even copy this and then paste it, and then I can show you, I can stylize it, make it red. Okay, the point is that if I take this thing and I move it over by 2 pi, well, I get something which is then again overlapping. Okay. Of course, I didn't draw it very well, so it's not that good. All right. So that's what is happening here. What is the maximum current? Well, what's the maximum of the function? 400. I think milliamps. What is the approximate current at time t equals 4? Well, we can just plug 4 in to this equation. We'd get 400. We'd get 400 times cosine of 4 pi times t is 4. So 16 pi plus 2 pi is equal to 400 times cosine of 18 pi. Well, 18 pi is divisible by 2, so this is coterminal to 2 pi. Or 0, for that matter. So this is equal to 400 times cosine of 0. And this is equal to 400 because cosine of 0 is 1. So that's the approximate current when the time t is equal to 4. All right, now, how do we move forward? Let's come up with something new. Okay, sketch the graph of f of theta equals tangent of theta. Well, as I said before, we can do this by looking at the graphs of sine and cosine. So let me draw sine first. Here's 1. Here's pi over 2. Here's pi. And why don't I draw on also negative pi over 2 and negative pi. Well, if I draw on sine, I know it takes value, sine takes value 1 at pi over 2 and 0 at pi and 0 at 0 and negative 1 at negative pi over 2 and then 0 at pi. So it looks like this. And then it comes up and then we go up and then we go down and then it looks like this. So this is sine of x. And then cosine of x looks like this purple thing. It starts at 1 and then goes down to pi over 2 and then goes down to negative 1 and then pi over 2 and down to negative 1 on the other side. And it looks like this bell shape, right? So here's what cosine of x looks like. Okay, so tangent of x is equal to sine of x divided by cosine of x. So if I want to draw the graph of this function, what I'm going to do is at each point, like pi over 2 and pi and negative pi over 2. In fact, why don't I spread it out a little bit more? I'll do pi over 4, pi over 2, 3 pi over 4, and pi. Be right here. Negative pi over 4, pi, negative pi over 2, and then negative 3 pi over 4, and then negative pi. Okay, then what do we have to check? Well, we just have to check what's happening with these functions, right? We have to check what is happening with these functions. Okay, so let's start at 0. What do we want to do? We want to take the height of the sine function and divide it by the height of the cosine function. So tan 0 equals sine 0 over cosine 0, which in our case, the height of the sine function at 0 is 0, and the height of the cosine function at 0 is 1. So we take 0 over 1 and we get 0. So we plot the point 0, 0. So the input was 0, then the output was 0. Now let's try tan of the next kind of interesting point is, well, there's a point here where these two things are equal to one another. That's the height root 2 over 2, and this occurs when theta is equal to pi over 4. So we can try tan of pi over 4. Well, the height of the cosine function, or sine function, is root 2 over 2. The height of the cosine function is the same thing, and we get 1. So at pi over 4, the height of the tangent function is 1. And then what happens as x increases from there to pi over 2? Well, what happens as x continues to increase is that the sine function is getting close to 1, and the cosine function is getting close to 0, but positive, which means that our value of tangent is going to actually be going up to infinity. So it looks something like this, and we have a vertical asymptote at pi over 2. Okay, now let's check what's happening on the left side. Well, on the left side, okay, again, we are going to have a point at, say, negative pi over 4, where this height of our cosine function is the negative of the height of the sine function. Okay, so in this case, we're going to get tan of negative pi over 4 is going to be equal to, well, the sine function will be negative root 2 over 2, and the cosine function will be root 2 over 2, and this will be equal to negative 1. So then tan looks like negative 1 at negative pi over 4, and again, as we get up to negative pi over 2, we're going to have a vertical asymptote. But this time, what happens as we get close to pi over 2 is that the value of sine is getting close to negative 1, and the value of cosine is getting close to 0, but positive. So if we divide something positive by something negative, we get something negative. And as that denominator goes to 0, our number is going to blow up. So we get an asymptote. Okay, and then again, beyond this, it just repeats, right? It's just going to repeat again. So we're going to have another value of 1 there, and it's going to go up like this, right? Again, same deal on this side. We're going to come down to negative 1 and then go through, and then down like that. Okay, so it's just going to keep repeating like that. And we can see now, if we want to understand what is the period of this function, well, we just need to check what is the distance between 2 points which are going to be guaranteed to take the same value. It might be easier if we chose another point. Why don't we choose this point here? Move it over till we find another point with the same height, and we check the distance between them. Well, the distance between 3 pi over 4 and negative pi over 4 is exactly if we subtract the 2. And we get 3 pi over 4 minus negative pi over 4 is 4 pi over 4, which is equal to pi. So the period of the tangent function is actually pi. This is also the period of the cotangent function as well. Okay, so those are the two functions which we have, which are going to be pi periodic. Everything else is 2 pi periodic. Okay, so next up, we're supposed to identify 3 values of theta for which tan of theta is equal to 0. Well, tan of theta is equal to sine of theta divided by cosine of theta. A fraction y over x is equal to 0 only when the numerator equals 0. So tangent of theta is going to be 0 whenever sine is 0. And we know that tan theta equals 0 if and only if sine theta is equal to 0. And we solved this in class. This meant that theta was equal to n times pi, where n is an integer. So the reason why tangent theta takes values 0 at the same places where sine takes 0 is because sine is the numerator in tangent, right? If the numerator of a fraction is 0, then we'll have like 0 divided by some other number is always still 0. Okay, and then 3 values of theta for which tan of theta is undefined. Well, it's going to be undefined at any of these asymptotes here, such as negative pi over 2, pi over 2, 3 pi over 2, ... And we find that the cosine value of all of these functions, of all of these angles, we have cosine of negative pi over 2 is equal to cosine of pi over 2 is equal to cosine of 3 pi over 2 is equal to 0. So why is tangent undefined at these points? Well, it's undefined because we're trying to divide some number by 0. And that's an operation which we specifically choose not to define. You can try to define it if you want. You can say that something divided by 0 is 10. But all of mathematics will break if you do that, so I don't recommend it. Okay. Find the value of all 6 trigonometric functions. We've done this a million times. I'm going to skip that one. I'm also not going to ask you to graph those functions. So I won't ask you to graph secant. I might ask you something about their graphs, but I won't ask you to draw a graph of them. Or I might ask you things about these functions, but I probably won't ask you to graph one. All right, let's do another one. Well, we've got cosine of phi is equal to negative 0.3. We're supposed to answer in which quadrants can phi lie? Well, we don't even have to use the same method as before, which is, to draw out those things and ask, okay, well, what is the x value and which points have x values with that sign? Okay, instead, what we can do is we can just remember our good old friend ASTC. And ASTC was to tell us where all of the trigonometric functions are positive. So all trigonometric functions are positive in the first quadrant, sine is positive in the second quadrant, tangent is positive in the third quadrant, and cosine is positive in the fourth quadrant. So if cosine is negative, then we know we're definitely not in the region where all angles, all trigonometric functions are positive. And we know we're also not in the region where cosine is positive, because cosine is negative, right? So we know we have to be in quadrant 2 or quadrant 3. It's another way of thinking of it. All right. So then next up, another problem. We're supposed to ask, well, tan of rho is positive. Again, we can use the same logic, ASTC. Tangent is positive. That means we're either going to be in the A region where all trigonometric functions are positive, or we're going to be in the region where tangent is positive. So this is going to be 1 or 3 for rho. And if tangent's negative, well, again, we make our ASTC. We know we can't be in region A and we can't be in region T, because then tangent would be taking a positive value and it's taking a negative value. So we know that sigma should be in quadrants 2 or 4. So we don't even have to necessarily go and draw these lines and figure out where they intersect the unit circle. That's a perfectly fine way of thinking about it. But we can also, use all tools which are at our disposal. And ASTC is one thing that we should definitely remember. It's very useful to know where these functions take positive or negative values. Okay. And they just take, we only really have to learn where they take positive values because they take negative values everywhere else. So as long as we know, there's a bird like right outside my window. Sorry, easily distracted. Okay, so as long as we know where they take positive values, we also know where they take negative values. Okay. Use your knowledge of the unit circle to answer the following. You want to find two distinct angles theta for which sine of theta is equal to the square root of 2 over 2. Okay, so what am I going to do? I'm going to do what I did before. I'm going to draw a unit circle. And I'm going to consider the line y equals root 2 over 2, because remember, sine is describing the y value. So if y is equal to square root 2 over 2, I'm going to draw in a line here, which is that line y equals square root 2 over 2. And then I can see that there are 2 points which are going to satisfy the fact that they're going to have this y coordinate. There's going to be one which is here at the point question mark comma root 2 over 2, and another which is going to happen here at question mark comma root 2 over 2. You probably already know what the question mark is, but I'll show you how to figure it out anyways. We have a triangle here, and we know that this length is 1 because it's the radius of the unit circle, and we know that this length is root 2 over 2 because it's the y coordinate of that point. And if we look at the ratio between these two, we can tell that if we multiply 1 by square root, or if we multiply this guy by square root 2, then we would get 2 over 2, which is 1. So we can tell that the difference between these two is by a multiplication of root 2, which tells us that this is a 45, 45, 90 triangle. Likewise, on the other side, we have another triangle. We know from its side lengths that this is a 45, 45, 90 triangle. And so we don't actually need these question marks in here. We can fill in, these are the points square root 2 over 2, comma square root 2 over 2. And the other one is the point negative root 2 over 2, comma root 2 over 2. And now we need to figure out what are the angles. Well, the first angle we want to know is what is this pink one? It's 45 degrees, so let's give it in radians, pi over 4. Or we'll do another one with I don't know, purple maybe? The purple angle is the angle here, which goes to this terminal side. Just a little bit more subtle figuring out what that is. Well, it looks like a 45-degree angle plus a right angle. So that's 45 plus 90 is 135. Or you can think about it as 180 minus 45. Right? So that angle is going to be theta is equal to, well, pi would be all the way to the left side. So I go 3/4 of the way. So 3 pi over 4. So those are two distinct angles for which the sine function gives the value √2/2 as an output. Okay, now we want to find two distinct angles, phi, for which cosine of phi is equal to the square root of 3/2. Okay, so in this case, we've got another unit circle. Only here's the deal. This time, cosine is the x value. So we want to know which x values which points on the unit circle have an x value of the square root of 3/2. So I'm going to draw in the line x equals square root 3/2, and I'm going to find those 2 points. Well, the first one's right here. And it's we've got a triangle in here. And what do I know? I know that this length is square root 3/2. And this length is 1. That tells me that the other length should be 1/2. And this angle should be 30 degrees. And this angle should be 60 degrees. Then the other one, blue with blue. It's another angle here. And we know that this length here is square root 3/2, and this length here then has to be 1/2, and this length here is 1, and therefore the angle measurement, which is across from the shortest side, is the shortest angle. The angle measurement, which is across from the medium side, is the medium angle, and the angle which is, or the side length, which is across from the 90, is the largest side length. Okay, so these are the points. These are the angles then. Theta equals 30, or theta equals negative pi over 6, all right? Or with red, theta equals just regular pi over 6. Okay, a 30-degree angle is equivalent to pi over 6 radians. Okay. Graph y equals sine theta. We've done this a million times. Pi over 2, pi, 3 pi over 2, 2 pi. Go up, then down, then up. Down, up, then up, and then down. Okay, so here's sine, and we're asked to find the following. We want to know a and b such that in between a and b, we will get every single output with no repeats. Every single output with no repeats. So we want to consider basically the following. we want every single y value between -1 and 1 to get hit, but only one time. So I just go over until I hit it once, go over till I hit it once, go over till I hit it once, go over till I hit it once, and so on and so forth. But I don't want to go any further over, because then I would get another point which would replicate a value which I had already gotten. So I just do this, and then on the other side I do the same thing. Go over, and provide an interval in which sine takes all of its values exactly one time. So the interval that I should give should be -π/2, π/2. But I could give another couple of intervals if I wanted to. I could also give the interval from, say, π/2 to 3π/2. That would also be valid. Let me do that one in green. So then I would have all of these values would get hit on the left-hand side, and none would repeat. And then on the right-hand side, all of these values would get hit, and none would repeat. So I'm looking for a region where basically the function is 1 to 1. That's what it's asking. Okay, and if we have cosine, well, we have to adjust a little bit, because cosine, you know, looks like this. Oh, come on. I'm so bad at drawing these. Cosine looks like this, and up again, and up again. So we want to just choose a region where we hit all of our inputs, or all of our outputs, and no repeats. So I'm going to choose between these two bars. So like 0, π would work. Or we could also choose between these two, which would be something like π, 2π would also be fine. That's this region. And the red region is our 0π. So this is really asking you if you understand how we can restrict the domain in order to cause the function to be 1 to 1, which is what is required in order to compute arcsine and arccosine. We need to understand that we're only going to work on the right half of the unit circle. In other words, we're only going to consider this domain here. We're only going to consider this region between -π/2 and π/2 as our domain. And in that region, our function is 1 to 1, so we can talk about its inverse. So that was -π/2 to π/2. Okay, so I think that is all I wanted to talk about on this review. So if you're watching the YouTube video, don't forget you can also go to the SI session tonight. I think it's from 6 to 8 p.m. with Jamie and the Blackboard Collaborate Ultra. So please check that out. If you have any further questions, you can email me. Your exam is tomorrow. It's due at 9 p.m. So make sure that you get it submitted as a single PDF file to Blackboard no later than that time. I will post the exam at 8 a.m. so that you have plenty of time to work on it. It's open note. Please do not collaborate with any other human being other than myself. And yeah, happy studying and have a good day. I'll see you guys all on Monday.